Welcome to APEC. It's June 11th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Shreesh Holla will present on the Quantumloop field propulsion technology. Jim Buckeyne will propose a mathematical model for quantized weight, and David Perez will discuss the variable electromagnetic drive. Mark Sokol and Aidan Schaffer will provide detailed lab updates in preparation for their upcoming experimental marathon, and we're going to be finishing off the event with an open discussion and ad hoc presentations by conference attendees. So, the normal quick reminders here. You can view our conference replays, details, and speaker info on our website at altpropulsion.com. Again, that's altpropulsion.com. Please save those questions for the Q&A session after each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. And I'll repeat that throughout the conference. That just makes it a heck of a lot easier for us to answer questions. You can also type those questions in the chat. We will go through them after each presenter finishes. So with no further ado, let me introduce you to our first guest today. Shreesh Holla is going to be talking about Quantumloop, a breakthrough field propulsion technology that functions as a unique thermodynamic non-equilibrium heat engine for anti-inertial propulsion by harnessing inertial vacuum energy. It's a highly scalable electric propulsion technology for high-speed, extremely low power consumption propulsion. Shreesh is going to discuss how it works and what makes it so unique. So without any further ado, I am going to place the spotlight on Shreesh, and I will ask you to unmute, sir.
So as Tim mentioned, firstly, Tim, thanks for inviting me to this. It's a great opportunity, and looking forward to talk about Quantumloop. And anyway, here we go. Quantumloop is an anti-inertial propulsion technology. So I don't have an agenda slide, which I should have, but basically I'm going to give a high-level overview of Quantumloop. And then I'll get into a little bit of the state of the art and that kind of thing. And then I will get into more details on the technology and the science behind it, and where we are at this point in time. So this is the high level. So it's an anti-inertial electric propulsion technology. So no reaction mass is needed. So basically the inertial vacuum background moves the vehicle directly. It is highly scalable because it's using ambient energies for propulsion. And there is some activation energy required to create the reactions inside. So that's quite trivial, which I will explain as we go forward. So theoretically, very high speeds based on an accelerating propulsion profile. And again, because it's anti-inertial, really speaking, theoretically, any axis propulsion should be feasible. And here's a kind of, I don't know how relevant it is for this discussion, but it's basically autonomous operation does not require anything because the engine itself can be configured to go in any direction. So Quantumloop technology. So again, so it's a thermodynamic non-equilibrium propulsion engine. It's based on this concept of anti-inertial thrust, which is an entropic thrust sustained by inertia. Okay, the engine itself is based on an optomechanical kind of heat flux system, and it is scaled by high frequency of these effects. So basically, it's a unique propulsion technology since it's harnessing inertial fields in an assistive manner. Okay, and so basically, it's an unconventional kind of a nonlinear propulsion system because there's a certain non-equilibrium that's caused within the engine, which is measured by the vacuum, which produces propulsion. So a little bit of details. So basically, there's a kind of a virtual force which is converted into system momentum through our technology as a non-Newtonian type of propulsion. Okay, it's a second law of thermodynamics, which I will get into more detail. So we basically virtualize Newton's laws in a thermodynamic manner, which is made physical through this anti-inertial body force. Okay, and so basically the energy momentum is exchanged by space, as I mentioned, through the inertial vacuum background. And so energy for propulsion is coming from the vacuum background. Okay, so what we are really calling this thing as, it's a momentum machine, which is basically driven by momentum and not by a force, which is what we have conventionally in Newtonian physics, right? So as I mentioned, high frequency is a scalability option that we have. And here I just, this diagram, I think it's there on my website too, if anyone has seen it. But basically, I kind of show that, there is something that's happening inside the yellow box measured by space, which produces propulsion. I'm just not focusing too much on this because I think everyone would want to know more of the specific details. So I'm just going fast here. So just, I'm sure most of the people here know about this. I mean, all propulsion today is Newtonian. So basically, we throw things out the back, different kinds of things, and it moves, really speaking. There's field propulsion, like solar, electric, magnetic sails. Of course, in the terrestrial, we have wind for marine. So there's various propellantless propulsion technologies which have been proposed. There's these inertial propulsion, beam drive, gyroscopic, etc. Just completely disregard those. Then there is asymmetric capacitors, but that didn't really work out too much, I believe. Photonic rockets, where basically there's a laser that is emitted, massive lasers emitted to the craft and spacecraft. So I think there's a lot of research going on in the academic and at various institutions, NASA, etc. EM drive, I'm still not sure if it amounts to anything much, really speaking. Then there's Mach effect thruster, which I think is doing well in terms of propellantless technology. I still don't know. I've never really understood how that handles conservation of momentum, but it's going along. So anyway, this is just a snapshot of. I mean, there's a host of other technologies that are there. I mean, including that have shown up at APEC and other places. I just want to give an introduction. So this is my opinion about propulsion problems. I mean, most new approaches are focused on the inside, and which I believe is more of an engine generation issue, and they do not focus too much on the external, because propulsion is about moving against the world, so to say, or the earth, or space, etc. So that is more important than what is inside. Field propulsion, of course, there have been various theories, but I don't believe there's been enough work in this area. Maybe because people are more concerned about what's inside, maybe, I don't know. And there's GTR theories, which like wormhole, Alcubierre, I believe they are still at theoretical stages right now. So here's my vision for next generation propulsion, really speaking. So basically, field propulsion, harnessing field energy, preferably non-nuclear, but I don't know if that's feasible. Of course, it needs to be green and clean, given its field propulsion, really fast, and basically high payload mass capacity. And ideally, we want it to be universal, not just for space or not just for certain specific terrestrial applications, and needs to be highly maneuverable without kind of breaking the bank, so to speak. Okay. I need to make some changes here in that view. Kind of hides everything. Okay, I think that's good. Okay, so the next two slides is important to understand the quantum loop technology, because it's the foundation of Quantumloop. Okay, so the first is the superstring propulsion. So I've just captured a snapshot of Minami's um, uh, proposed superstring propulsion. So basically, what he claims is um, if there's an entropy gradient within a spaceship or an engine, really speaking, there's an entropic force from the superstring vacuum background as a body force. But this does not produce propulsion because space and the spaceship are held in place due to the act of emitting entropy at the ends, really speaking. Okay, and the action of the vacuum, the superstring. So what he claims is if you relax it, so basically a high frequency relaxation of the engine, you can get momentum as a superstring relaxes, really speaking, okay, due to the finite time relativistically taken for the superstring to reach equilibrium. So from my analysis on this, this may be a problem because this relaxation still is in equilibrium with the spaceship. So I do not see that there's any way we can still produce momentum, really speaking. And second thing is this one is a body force. So any momentum that is achieved is still a body momentum. So we're not going to really see much of propulsion, really speaking, or none, as per conservation laws, etc. And that has been some of the comments on his theory, really speaking. So what it reads is Pinero's theory, which is the next slide for system momentum. So I've just included a link here for anyone who's interested in knowing more. So Pinero came up with a symmetry breaking method, really speaking. As you can see, the diagram is pretty simplistic what he has, but but basically this is the concept, really speaking. So he's saying if there is thermal gradient, as you can see, this thermal gradient between the ends of an engine, the engine is under non-equilibrium, and there is a momentum between the ends, as you can see this V1 that he shows, and there's a velocity space entropy gradient at either end. There's a net system momentum of this inertial vacuum background. Okay, so basically what I've deduced this as it's a separative change in momentum at the ends due to the thermal gradient of this VSEG. That is my short form because it's kind of difficult to keep on saying entropy space. Velocity space entropy gradient. So it's basically a separative total conservation of momentum. So basically we got momentum at the ends, and since they are asymmetric, the only way for the system is to conserve momentum is through momentum, actual system momentum, which has to be provided by the inertial vacuum background. Okay, again, I've linked the this theory here. Okay, so that's the background. So in terms of the technology itself, and this is a snapshot of what it is. So basically it's PNSB, as I mentioned, that's Pinero self engine, which is produced of the MSFB, which is Minami's theory, scaled through a unique Doppler shift. Okay, so the MSFB itself is produced through a unique entropy gradient method that we use based off a thermo-inertial domain thermodynamic non-equilibrium method. So then the superstring vacuum momentum is achieved of MSFB by basically Doppler heating of the rubber-like superstring, really speaking. Okay, and it's asymmetric by definition by the PNSB thermal model, and so we get the the VSEG. And because we have the VSEG as per Pinero's theory, we get system momentum, as mentioned before, which achieves thermodynamic equilibrium. So a little more detail on this. So basically we base it on a concept of an inverse Newtonian laws. So it's basically the right-hand side satisfying the left-hand side, MA is equal to F, the reaction needing an action force, really speaking. Okay, so that's basically the basis of how this works, and it's based on this virtual Newton's laws, which I kind of mentioned before. So what I mean by virtual is a thermodynamically valid state without the dynamics in there, which is why it's virtual, which is made physical through this combination of MSFP and PNSP. So what we're referring to this as a superstring sail. So basically, it is based off the superstring vacuum inertial background. Okay. Theoretically, it should be universally relevant and extremely scalable due to the superstring basis. As I mentioned, the Doppler shift is what scales the energy requirements as we go through accelerated propulsion. So that is through a kinetic energy Doppler effect. Okay. So here's my view, and this is, of course, questionable, of course. Normal Newton's laws are the vacuum provides the laws, and we supply the energy, as we know very well, right? Energy storage in some form, right? The inverse Newton laws is, of course, inverse. So basically, we supply the laws, not new laws, the same laws, but we need to supply the capacity for those laws, and the vacuum provides the energy. That explains the energy efficiency that I'm claiming. So this is a high level concept of the design. So basically we have a spring in place of Pinero talks about particles, but basically we use a spring to scale the technology, really speaking, producing the same momentum at either end. There's a method to produce an entropy gradient at either end. This is again different than Minami's theory. Minami talks about one entropy gradient through the entire ship. So what we are doing is we have an entropy gradient method at either end, really speaking. Okay, and okay, so I'm just going to get into a little more detail here. So if you look at one, is basically the classical. There's some force within the system, within a closed box, pushing on it. Of course, conservation of momentum. You get the dotted arrow on the left. Nothing further there, right? So what Pinero is telling is, if at these ends you have this V-seg, which is asymmetric, that's when you get momentum. Okay, system momentum. That's where the symmetry violation occurs, really speaking. Okay, because as you can imagine, otherwise we have Newton's third law, which would basically leave no external momentum, really speaking, right? Which is what Pinero also talks about in terms of a canonical momentum. If you have the same, if you don't have a thermal gradient, then basically it's the same as any closed box. So basically, the way we're doing it is so if you look at two is basically a Newton's third law, but using the superstring force. So because of the conditions that we've created, there is an entropy gradient. So instead of the normal reaction force, we have the Minami superstring force acting as the reaction force. But due to the existence of this entropy gradient, actually it's reversed, as I mentioned, it's inverse Newtonian. So basically the superstring force acts as an action force, and the internal forces that you see here is now become the reaction force. Okay, so then as Minami says, we have to relax it. So once we relax it, we get we should get momentum. That is what 3 shows, really speaking. So basically we get momentum here at either end, really speaking. And as I mentioned, just using Minami's theory is for relaxation is theoretically feasible, but from my understanding, it requires some seriously large volumes for anything usable, really speaking. And that's why we are using this thermodynamics of the D-brane, really speaking. Okay, so that's what I mentioned, the rubber-like thermodynamics of the D-brane. Okay, now, as I mentioned, if they are asymmetric, which it must be because of the temperatures at either end, we get the V-seg, and so as per Pinero's theory, we should get net system momentum in maintaining conservation of momentum or translational symmetry. Okay. So the way this works is this relaxation, just to clarify this point, these are the entropy gradients that I mentioned, just a kind of like a block diagram to show what it is. But there is some way to switch them off, really speaking, and that starts the relaxation process through time. And that's how we get what you see in 3. Okay, and so that's when you get propulsion, which is now the blue arrow that you see down here is propulsion because of conservation of momentum. So I've kind of so one of the things is I've been kind of modeling this as a or saying that once you have momentum here, you should have an inertial force, really speaking, which is of course in reverse. So that is what is the inertial vacuum background, which produces momentum to this side, which is the direction of the blue arrow. Okay, so here I'm just kind of it may be evident to some of you, but basically I want to show how this works. So the energy of rubber that Minami mentioned. So I'm just showing that. So basically you have the normal D brane, and then you have the stretch D brane as when the Minami superstring force occurs. Then we have the compressed D brane, which is basically either achieved through through Minami's relaxation method, or as I mentioned, through our thermodynamics, so where we heat the D brane, really speaking. Okay, so that produces a velocity of the D brane, as we know from rubber thermodynamics, which is now a VSEC, and so we get Pinero's conservation of momentum, total conservation of momentum. So just to clarify what I mentioned in 1 is, if there was no such thing as the VSEC, then it's just basically a very well-known box of forces. Okay, so a little more in depth on how this works. So basically, equation number 1 is basically showing what Minami talks as an entropic force, really speaking, through the superstring. Equation 2a is basically Pinero's theory. So basically, he says when you have P1 and P2 momenta at either end, then there is a momentum of the vacuum background. And this is through a velocity space entropy gradient, the delta Vs, and based on this, based on the entropy gradient at either end. Okay. So what he says, this must be a change in the system momentum by the inertial vacuum background, which should be the delta rho 1 rho im called. Okay. So this continues occurring if it is sustained, continues occurring as you can see in equation number 3. So delta rho v by delta t must be equal to system acceleration, really speaking. And so basically we can, if we can have the delta rho v itself, changing at the same rate as a certain frequency of activation, then we get that level of frequency, that level of momentum. As you can see, there's no force here. Okay, so this is the notion that I mentioned some time back. It's a momentum-driven propulsion. There's no force involved here. Okay, so to scale this delta rho v t, then we basically 2a needs to be monotonic, of course, which is quite evident. So then the last one is basically showing the basis for the thermodynamics of the D brane that I mentioned. So basically, KQ is as an internal quantum loop factor. FEI I mentioned is the superstring force, and you see the 1 by T, 1 by T. So it's an entropy gradient, really speaking, for at an end, really speaking. So just basically summarizing here, right? So we have the rho I, which is the rho 1 and rho 2, which is asymmetric. And so there must be some manner of correcting that asymmetry, which is rho v, which is what Pinero claims. So here I just want to draw it like basically what I can see as Pinero's theory is basically connecting MSFP, actually speaking. It can be seen as a combination of Newton's second law and an entropic force as you transpose factors here, really speaking, as you can see in the second line. Okay, but this again does not produce any momentum because any system momentum, because this is still a body force, body momentum. So it's still on the system, so to say. We need the full PNSP, as mentioned before, to see any system momentum. Okay, I just wanted to give a little more details as much as feasible at this point of time. So basically, as I mentioned, the hardest problem that I've had is basically the entropy gradient of Minamis, actually speaking. The issue, really speaking, is that it needs to be measured by the vacuum. And normally we have second law of thermodynamics, which would invert any entropy gradient anyway. So the solution was basically determine a way to basically pause second law of thermodynamics itself for that momentary period of time by pausing entropy generation. Okay, so that basically results in a thermodynamic non-equilibrium state. Okay, so so basically Minami occurs and the whole quantum loop reaction occurs to re-enable this second law of thermodynamics of the D-brane increased D-brane entropy, which achieves thermodynamic equilibrium. Okay. So the other big problem is a body force. So Minami claims that this is a body force, but we can't have a body force which is occurring from the outside to suddenly become part of the dynamics of a system, really speaking. So so this was the other hard challenge in trying to mix delta SR and this body force notion that Minami claims. So this is where the virtual Newton's third law really comes in. So basically, create a thermodynamically valid dynamic state, in terms of thermo-inertial behavior, which basically shows that there's a reaction force, but there's no action force, as I kind of mentioned before. And so MSFP, the superstring entropic force, can occur as the action force. Hence, also the inverse Newton's third law. So action is occurring before the action is occurring on the reaction, not the other way as it's normally known. So this can occur because of this non-equilibrium, because of this delta SR. Okay, so then the relaxation is under one problem, really speaking, because we need to have high frequency operation of the engine, but we are talking thermodynamics also out here. So we have a finite time of relaxation required, but if we stretch it too long, then the second law of thermodynamics will kick in to some other means. So there's a bit of problem there. So we use photonics methods to do that. So basically, this is a very important part, really speaking, because normally you can't just switch off a reaction force or an action force, really speaking. I mean, rather you switch off the action force, the reaction is also gone, really speaking. Okay, but in this case, we have one side existing and suddenly we switch off the MSFP, which means there is some reaction that needs to occur to counter that. There's momentum of the MSFP while the normal reaction force can start occurring again. So this is the other part. This is the part of Pinero's theory now. So I think I mentioned this a few times. So basically the rubber entropy, so we basically we insert an entropy gradient through photonics to achieve this rubber, this heating of the stretch D-brane, as I showed some time back in terms of equation number 5. And so again, this is again a virtual Newton's second law, as I mentioned. There's a thermodynamic state which indicates momentum is actually occurring, but it is not occurring, really speaking, which is now solved as an MA is equal to F, really speaking, because F is a body force, really speaking, right? So, but it occurs as a rubber-like momentum on the deep brain, or velocity of the deep brain. So as I mentioned from equation 5, there's the 1 by t there. So that requires infinitesimal heating, really speaking. Okay, but I mean, that's something that's very well known from rubber theory. So that's quite well known in that way. Okay. So one of the challenges also that I've been facing is the VSEC that I mentioned. That's the delta VS needs to match the rho V, really speaking. Otherwise, if you're scaling rho V, you got to scale the delta VS also, really speaking. So the approach for that I've been working on is using an acoustic Doppler shift for this, just because we need to have it needs to be linear, really speaking. So basically, this slide really shows how I'm claiming that kinetic energy can scale the propulsion over these Doppler shifts. So the actual scaling, well, of course, the conventional way would be, really speaking, an input force. Just put in more force and we should get more propulsion theoretically. Okay, possibly the thermal gradient also can be used to scale it up, really speaking. I've not really experimented too much with that, and that's planned. But theoretically, that should also provide enhanced propulsion, really speaking, from Pinero's theory. Okay, but definitely, if you reverse the thermal gradient, what I'd shown before, you should get reversed propulsion, really speaking. But I think the big thing, really speaking, in scalability is this frequency of activation that I mentioned. In a previous slide, I mentioned NT. So basically, that equation 3 indicates a linear relationship between delta rho V and the frequency, really speaking. So as an example, theoretically, we have 1 Newton being produced at 1 kilohertz. So what this means is 1 Newton produced 1,000 times a second. We should theoretically get 1 kilonewton scale through the to the D brain, really speaking. So basically, I don't think this is 1 kilonewton, really speaking, and this is just so that since we all understand newtons very well and forces, but as I mentioned, this is a momentum-driven propulsion. So the reason this would work is because of the MA that is being produced through the heating of the D brain. So basically, each Newton of force that is there, as an example, needs to satisfy the MA, and so we have this inverse Newtonian MA that really makes it work. Okay, but yeah, basically based on that, the energy needed is really for 1 Newton, really speaking. So that theoretically is a massive amplification of power output. Again, the efficiency, I'm sure this must be evident. I mean, since we're talking about energy being inserted into the system by the superstring vacuum, it must be greater than 1. And given the kinetic energy Doppler shift, this efficiency should continuously increase through system velocity. Okay. And again, this may be a little bit smaller in terms of the other two, but based on how we control the asymmetry, we should get an increase in efficiency too. So just summary kind of thing, value proposition. I mean, I think this should be evident. So basically, it's an anti-inertial propulsion, so it's propellantless. So for terrestrial needs, we don't need any propellers, etc. So that should also be a significant energy gain because we're not rotating heavy air or water, as an example. Again, as I mentioned, it's very low power needs. So it's highly decarbonizing propulsion, whether it's terrestrial or extraterrestrial, so to say. And as I mentioned, it's theoretically it's bidirectional. Not theoretically, this should be possible. And basically, by controlling the internal momentum, really speaking, we should get almost any direction propulsion. And direct propulsion, okay, that's fine. Okay, it's kind of evident, right? And of course, should be lower cost, should be relatively simpler to construct, and theoretically it's usable in any environment, really speaking. I still don't know if it'll work under water or under fluids, really speaking, but definitely surface transportation, air, space should work quite well. And this has been my biggest peeve about propulsion today. It is just keep putting more and more energy in, and so I like to look at this as an intelligent propulsion technology, which basically is not just yet another third law solution. So summarizing what it is, so basically constant force, constant acceleration, and constant energy. Inverse Newtonian model satisfies symmetry laws, as I mentioned many times before. Scale due to the ambient energies, and should work anywhere. And I don't see this working in a stationary or rotational manner, really speaking. I'm not really thought of that, but it is meant for propulsion, really speaking, linear propulsion. So as I mentioned, it's a momentum machine. It is not a conventional Newtonian machine, not an energy machine. And so given it is an inverse Newtonian, I would call it non-Newtonian, but theoretically in the end it is Newtonian, really speaking, because of the conservation of momentum aspect of thin arrow. But yeah, it's controversial, of course. I think everything that comes up here on APEC is controversial, so that's nothing new. So where are we right now? So basically, it's about TRL4. Most of the things have kind of have been proven. There's still some more work on some of the engineering issues in terms of had some various alignment issues with those springs, etc. Then some of the Doppler shift algorithms are still in progress, really speaking. Material design is pending, really speaking. I mean, definitely looking to get more into that because that's quite important for this kind of thermodynamic system. Because once we get there, we want to get more detailed tests, and so more study is required, and the photonics are required, really speaking right now, because right now I'm using, simple laser and LED array, really speaking. So I need to study that more. So the other thing is compute. I mean, given the, all the complex algorithms and timing and frequency needs, I'm running it off an Arduino, and I've been able to max it out at about 20 hertz. That's about it. I really, to get some serious scale, we need to go beyond that, but which is not possible in software. We need an FPGA or something similar for that, really speaking. But that's not feasible at this time. Maybe sometime in the future. Okay, and yeah, the simulation. I've not really gotten into it. I think that's a really complex problem, really speaking, given its non-linearity, the thermodynamic non-equilibrium, and all that stuff. So it's the to-do, really speaking. And at some point of time, we will have to get into some external validation. And okay, myself, I'm a mechanical engineer. I've been in various different areas: automotive, satellite communications, and consumer electronics. I've been an engineer. I've been product manager. I've been a few companies. I've been in Qualcomm. I've been at Lucent, Alpine Electronics, etc. One advisor who comes from GM, and he's recently retired, I think, over the last year. So been quite helpful. Also a member of LACI. I don't know if anyone knows about this, but LACI is a clean tech incubator in LA, and I'm part of the innovators cohort there. So yeah, summary part two, really speaking, it's a unique breakthrough propulsion technology. It's been there for about over 3 years of R&D, really speaking. I think there's a lot of new things that we could not do would become feasible once we have better progress on this. And of course, I'm open to, the right people, organizations, etc. And just a little bit of, I think I've talked about this. I'm not really going to dwell on this, but basically, given that it can achieve anything, I just kind of called out the different places it can be used. Okay, that's it.
Wonderful. Wonderful. Shreesh, thank you so much. Okay, so let me do this. I removed the spotlight. I believe that all of our spotlights are gone now. I'm going to stop the sharing. Perfect. Okay, so before anything else, I want to put this thing on gallery view. Everybody, please give a giant hand to Mr. Shreesh Holla.
Thank you.
A wonderful and in-depth presentation. That was really in-depth too. I was really amazed. Thank you so much. Thank you so much. So we're running a little bit ahead of schedule. So what I want to do is this. Let's go to our Q&A session.